so this is the general physics of what we're looking at here. So this is the laser, and it's putting out a Gaussian beam pattern, and we're profiling it at different locations. So for the laser, we're assuming the beam waste is somewhere in the laser source, and then we're sampling it at one position and then another position. Later in the lab, we insert the lens, and so that reproduces the Gaussian pattern over here. And so we're finding generally where the beam waste is, and then making sure to sample before and after that. So this is the process we did to test the beam profile. This is a general schematic of our spot and our knife edge, and we brought it across in 100 micron increments, looking at the notation of x being in that direction. The data should give us a plot something like this, where as we're covering more of the beam, it goes down like this. Taking the derivative of that will give us a Gaussian pattern.
So for this part of the lab, we took a laser at two positions, or a razor rather, at two positions. This position was position 1, and then we took the microscope and focused it on the razor blade and recorded that location so we knew exactly how far the second position was from the first position once we moved it. We then took the photo detector and put it on, moved it up here, and read the voltage as we moved the razor blade through the spot from the laser at 100 micron intervals. When we moved it back to a second position, we focused the microscope again on the razor blade exactly so that we would know the exact value of delta Z.
In the next part of the lab, we inserted a lens into the path of the laser to adjust what we were testing. To make sure that the lens was aligned to the laser, we placed it on a stage that could move in both X and Y and has tip and tilt, so there's 4 degrees of freedom. Then, to align the lens to the laser, we initially saw 2 dots on the laser surface. And so we moved it back and forth and up and down until the 2 dots were aligned. And then we used the tip and tilt to make sure that single dot was backfiring into the laser.
Okay, so to find the beam waste with the lens in place, we used a 200 millimeter biconvex lens, and we tried to put it at 2F away from the laser, so we would get a 2F imaging system, which would ideally put the new beam waste at the second 2F. So we put the lens at around 400 millimeters from the front of this, as measured with the microscope. And then we placed the microscope over here and found the beam waste to find when light came out, or at the beam waste, if the microscope was located correctly, the light would come out collimated. And we had a shear plate and a interferometer we could use to check that, which we would get fringes parallel to this line on here. This distance actually ended up being 290 millimeters, which is shorter than this distance, which would indicate that the beam waste is actually not right here, but somewhere inside the laser, so that this distance is longer, resulting in this distance being shorter. To find this distance, we focused the microscope on the front of the lens, not the back of the lens, because if we focus on the back of the lens, we would have to take into account the optical path length introduced by the thickness and refractive index of the lens.
After we had found the location of the beam waste, we knew that we had to place the razor blade both in front of and behind the beam waste to take our measurements. So for the first part, we placed it in front of the beam waste, and then we used the microscope with the laser turned off to find the exact location. We noticed that our readings were jumping around a lot and that we were getting a lot of noise and background, so we covered up our photodetector and our razor blade with a black shroud to sort of block out any scattered light.
So this is the first position without the lens, and this is the derivative of it, and you can see it sort of forms a Gaussian. This is the second position, and it also sort of forms a Gaussian. This is when we put the lens in. The data is not as pretty, and it sort of forms a Gaussian. And then lens position 2, and then for some reason this one, the lens created rings, and so that's why you sort of see 2 Gaussian patterns in there. Okay, so this is the explanation for all of the math that's involved to find the final answers. So our wavelength of the laser is 633 nanometers. In the experiment, we chose our delta Z, and from our data that we plotted, we determined the wastes of the beams at the 2 positions of measurement. If we wanted, we could find the standard deviations. This can be found, the wave number and the variable B. This giant quadratic formula can be solved to find the Rayleigh range Z0, and from that we can find the beam waist at the Rayleigh range. Additionally, with that we can find the numbers Z1 and Z2, which are the positions of our measurements relative to the Rayleigh range.
The beam wastes were found by looking at knife edge position when the normalized beam power was at 84% and 16%, and then subtracting the two values. These were our values.